I mean, the old stuff was like 300. So it was 50% harder, first try. Well, it was only because I knew that nickel aluminum and nickel titanium, or in this case nickel aluminum, they had a very strong affinity for each other. Both of them dissolved in gold copper alloys at a limited concentration. So if you heated them up at high temperatures, they should go into solution. At lower temperatures, they should join up and bond to each other in this nickel 3 aluminum. And they did, and we got high hardness and we got precipitation hardening. I went off in 1984 to Tokyo for the Navy, came back afterwards and said, well, what happened? Have you patented it? And they said, well, we decided there wasn't a real application for it. I said, oh. So they said, well, but can you make us age hardenable sterling silver? So I went and tried the same thing with sterling silver. First attempt was a failure. The second attempt, sterling silver is silver copper alloys. Second attempt, I added lithium and tin, and it worked. And the lithium and aluminum worked. Same type of principle. Lithium and tin form a high temperature intermetallic. They both dissolve in silver. And that, I said, well, what's the application for this? They said lightweight dinnerware, you know, sterling silver dinnerware. And so we went over to Reed and Barton, and it's like 1985, and we had our hard sterling silver, and Reed and Barton said, well, no one wants lightweight sterling silver dinnerware. They want people to know that they are rich and they can afford a lot of silver, and so lightweight sterling silver is not dinnerware, is not. So obviously this gold company, they're out of business now. They didn't do a lot of market research, but they did have an application, okay? Baby cups, you know, sterling silver baby cups. So if you go buy a baby cup today, it's 20% lighter because of my alloy. How about that? You can still buy it for 50 bucks, but they make an extra 10 bucks profit, okay? Because they got the strength up. Anyway, so these different alloys that go into these things, the solid solution strengtheners are cobalt, chrome, iron, molybdenum, tungsten, tantalum. The precipitation hardening, which they call gamma prime, is the phase. Aluminum and titanium. It turns out niobium also does that, but it's a gamma double prime, slightly different crystal structure. Solid solution strengthener is these alloys. And then they have all these carbides. Some things, chrome will form a carbide, tungsten will form a carbide, molybdenum will form carbides, niobium. So they throw in different carbide formers to harden things. And then they have what they call topologically close packed phases. It turns out they tend to be hexagonal close packed or more complex phases. Sigma, P phase, mu phase, and Laves phase, very brittle. And if you hold these alloys, some of these alloys at temperature for a long period of time, you'll end up with structure. This also happens in some of the stainless steels, and the times we're talking about are tens of thousands of hours. Okay, and that may have been one of the problems we had. I told you about my chrome moly tube over here at the Boston Navy Yard, and they wanted me to say, oh well, yeah, you can use stainless steel to weld it. But the Navy said you had to use Inconel. Well, it turns out the stainless steel probably after 10,000 hours formed this brittle phase and the things would crack. Okay, so it's a general problem. So far as surface oxidation, when these things are used at high temperature, it's chromium and aluminum are the primary things which form chromium oxide and aluminum oxide scales. If you analyze the surface oxide on these high temperature nickel-based superalloys in jet engines, they will be chromium oxide or aluminum oxide, depending on the ratio of the two, nearly pure. Just like stainless steel, it's nearly pure chrome oxide. On these nickel-based alloys, it's either chrome oxide or aluminum oxide, depending on the composition. Okay, so that's sort of an overview of the metallurgy of these things. We're talking about alloys that are going to cost $30 to $100 a pound, as opposed to steel at $1 a pound, roughly, for an alloy steel, like an HSLA steel. Considerably more expensive. Why doesn't the Navy go to make an Inconel submarine? Well, you can make one out of AL6XN and probably only pay 10 bucks a pound for the steel, okay? But why are you paying 10 bucks a pound rather than $1 a pound? And you really get down to, if you're going to build a $2 billion submarine, would you like to build out of steel, and the whole cost is, let's say, 500 million of that 2 billion. Okay. So if you have to make it out of all stainless steel, now you're going to talk about a $5 billion hull, right? 10 times the price. And so you just ordered 9 submarines for 18 billion, right? Would you have rather purchase 3 submarines that were non-magnetic? Okay. And why don't we build titanium submarines? Because the price of titanium as fabricated is probably, or the price of the titanium is probably $100 a pound. So you could have purchased, with $18 billion, 1 submarine. Okay? Now you have to ask, would you rather have a nuclear carrier or a nuclear submarine?
They also found problems with the titanium being irradiated, the neutron brittle or something like that. Derating some of the holes for the Russian subs that did that.
I'm not sure if it's radiation from the nuclear. It could be. I mean, that's probably beyond my classification. Okay, but what it was, in fact, and we can talk about this. Well, I can't. I might as well tell you the story now. So in 1980, I'm coming back from my first trip to Europe. I'm on the plane, and they hand out a copy of the International Herald Tribune, and I'm reading it, and there on the front page, or maybe it was the International Wall Street Journal, whatever it was, on the front page it announced that the Soviets now have a titanium submarine. This was the Alpha sub, okay? Maybe the Navy, U.S. Navy knew it a little bit earlier, but it was now on the front page of an international journal, or an international newspaper. I had been working on welding heavy section titanium since 1977, 3 years earlier, and so all of a sudden I come back and a number of people want to talk to me. Okay, because ONR had been funding me to weld heavy section titanium. Well, they had some conferences down at David Taylor in Carter Rock, and I'll tell you some more of those stories when we get to the titanium. But I remember the guys from the Naval Research Lab said, "Tom, how do they solve the creep fatigue interaction in titanium?" And I kind of shrugged my shoulders because I hardly even knew what the creep fatigue interaction was. But the Naval Research Laboratory knew. It turns out that if you compress titanium and hold it under compression, fatigue cracks grow really fast. Well, guess what a submarine hull is? It's held under compression when you're down at deep. And so there were several problems with the titanium subs of the Soviets. First of all, there were certain things that weren't a problem. They could go faster underwater than our destroyers could go on top of the water. They could dive deeper than the collapse depth of the depth charges. Okay, some of these things concern people. Although one person from Rocky, who did a lot of work for Rocky Flats, says, "Well, if you use the right type of depth charge, you only have to get within a few miles." I thought, yeah, and as soon as you start doing that, we have bigger problems. Okay, but in any case, so we could have gotten rid of them. But one is they developed these cracks, and they were noisy as could be. But they did develop the cracks, and so the real answer that I didn't know, that the people from NRL was asking me, how did the Soviets solve the creep fatigue interaction? And the answer is they didn't. They just built the ships, and then they found out about the creep fatigue interaction, which NRL had studied and knew about, and that was one of the barriers to our building a titanium submarine. Although the big barrier was cost, okay? And it really is a question of, do you want an $18 billion submarine, or do you want a, one $18 billion submarine, or would you like 9 steel ones or 3 stainless steel ones? Okay, or 3. No, 3 would be, 3 would be stainless steel. So, unless you want small ones, you can buy small ones cheaper, okay, than all of that. But that's the real problem with these things. Okay, one of the things you need to know about nickel-based alloys, and I already told you a little bit about it the other day when I told you that I only knew of one welding code out of Westinghouse Bettis, where they make Navy nuclear parts. They were welding some Inconels, and they were doing electron beam welds, and it's the only code I ever knew that would allow you to have cracks in your welds and pass the spec. They had a maximum size of the crack. I think it couldn't be more than about 1 millimeter in length. But what happens when you go up and heat up these nickel-based alloys, you have something called liquation cracking, which means it forms a liquid. And I've talked about having a Slurpee. You have solid crystals surrounded by liquid, and the stuff flows like a snow cone or a Slurpee, okay, at high temperatures. So here's your welding temperature time curve, and you have liquation when you get up in the heat affected zone in particular. It's not a uniform structure. You have segregation in the metal when you melt it and reform it. But even in the nickel-based alloys, and this occurs in the Monels. In fact, it might have been a Monel rather than an Inconel that I was welding for, or I was looking at the welds for Bettis. And so you have your solidification grain boundary, and you have your fusion boundary here. So you're in your heat affected zone. You have particles that will dissolve, liquate, turn to liquid during the heat of welding, and then some of those will segregate to the grain boundary, particularly in multipass welds, and they had to make an electron beam weld with a 30% overlap in this particular thing. And you get a grain boundary film that melts. And if you want to see what it looks like, here's a picture of microstructure of a nickel-based alloy. They call it solidification crack, but this is the base metal structure, and it partially melted along some grain boundaries, and some of the liquid in between these grain boundaries migrated, and they call this a self-healing crack. Well, this might be self-healing here, but these two weren't self-healing. They're still voids, okay? So it's not a great situation. Here's another picture of another alloy, and you've got the liquid coming in and forming this. You have other cracks here. Here's one you actually can see. This is the dendritic structure of, this is probably a Monel. Niobium rich, let's see, AB, what's the B? It's from John Lippold. John, aren't you going to tell me what you got? No, not going to tell me what the alloy is. Okay, but you can see these type of little nodules. Those are called dendrites in the steel structure. This is probably a cast nickel-based alloy, and the region in between is high in alloy content. It got rejected. These are high in nickel in the center of the dendrites, and out at the edge you're rejecting alloy content, so you have a more highly alloyed structure. And you can see you heat it up to weld it, and the stresses from cooling of the weld crack things. Okay, so nickel alloys, whether they be Monels, whether they be Inconels, are very susceptible to liquation cracking, high temperature cracking, due to the stresses of shrinkage. So if I can make a weld like this, and I get all my grains going this way, it pushes all my alloy content there. If I make an electron beam weld, then I can end up solidifying grains from the edges in, and have all my alloy content in the center, and just have a crack right down the center of the weld. Okay, so the shape of the weld makes a difference. Here's a fillet weld. This is good because you have the columnar solidification grains growing from the edge out and pushing the liquid out here. If you have something like this, you actually will collect it in the seam right here, and so the weld profile makes a difference. Okay, not just for fatigue. This would be a good profile for fatigue. This is a worse profile for fatigue, a higher stress concentration at that corner than this corner, but this is lousy for solidification cracking. You can get solidification cracking in steels, but you got to really try. Okay, store a lot of phosphorus in there, and you can crack a steel. But you know, if you go look at the literature, they'll talk about solidification cracking of steels. I don't know if I should say I've never seen a solidification crack in steel, but I haven't seen very many. Okay, and I talked about this the other day when we were talking about stainless steels. This is the Rensselaer Polytechnic Veristrength test, where you basically weld on a stainless steel or a nickel-based alloy, some high alloy typically. You make the weld, and as you're welding, you just bend the plate along the weld. It's called a trans-Veristrength test, and you can see when you applied the pressure, and you just open up the cracks. Okay, because the cracks were partially liquid. Okay, at the time, and you open it up, make more space. Any questions on that? Let's take our break. Okay, so why don't we? This is the